Welcome, welcome, beautiful people. How is everybody doing today? So let me go ahead and share my screen. Come in here. And this is going to be what? Your general physics. And we're going to be talking about chapter 3, which is going to be your energy. So just a little reminder. We started off this course by defining this placement, which we said is going to be your delta x, which delta, that means your change, and your x, that's going to be your position, which is going to equal to your x final, whatever x initial is. So this is your final position. And let me get a different color. And then it's going to be your initial position. Which is going to equal to, we said we gave it a letter D, and it's going to be an M for meters. Awesome, awesome. So we take this displacement, we divide it by T, which stands for your time in seconds. And we said that's going to equal to your velocity. And we give the velocity letter V, which D is for your displacement, which is going to be in meters per second. When we talk about velocity, we're talking about your average velocity, which is going to be your change in velocity divided your change in time, which is going to be your delta V. No, so there's going to be your V final minus V initial divided by your T final minus your T initial, which is going to be your average velocity. So it'll be your V final plus your V initial divided by 2. Now we took this velocity and we used it over some amount of time. So for velocity, you were at one point of distance at one point of time. You become a different point of distance at a different point of time. You take this velocity and you divide it by this time, and that's where you get your acceleration. And we give the acceleration the letter A, which is your velocity was in meters per second times the second that we have, which is going to make the acceleration as meters per second squared. And it's your change of velocity over your change of time, which is your V final minus your V initial divided by T final minus T initial. If you start from 0, that means this is your T final is going to equal to T, which basically means that your acceleration was going to equal to your change of velocity over T. Now, we took this acceleration and we used it on some kind of mass, which the mass is going to be in what? In kilograms. And that's what we talk about the force, and we give it the letter F, which is going to be your mass is going to be in kilograms, And your acceleration, we said, was going to be in meters per second square. So be meters per second square. And that's what we call the Newton, which we gave a letter N, which is our unit for the force. That's your mass times acceleration. Now, one of the forces that we actually saw, let me get a different color on this, was called your gravitational force, which we gave it the letter Fg, was going to equal to G m1 m2 over r squared. And G that's going to be called your gravitational constant was going to equal to 6.67 times 10 negative 11 meter cube kilogram negative 1. Now, we're going to see how we're going to take this force over here and we're going to apply it to some displacement, which is going to be your delta x, and that's when we're going to be talking about the work, which is going to be your W which is going to be Newton meters, which is, if you convert to newtons, we said it was kilograms meters per second square multiplied by this meter, the other meter that we have. And this means that the work is gonna be in kilograms meter square per second square. And this is what we call the joule, which we gave it the letter J, which is going to be our unit for our work. Now, so your work, by the way, is going to equal to force times your distance. So your work equals your force times your distance, but your force, we said, is going to be equal to mass times acceleration. So your work is your mass times acceleration times your distance. Now, we're going to be taking this work and we're going to apply it on some kind of time. And that's what we're going to be talking about, the power, which is going to be joules per second. Actually, let me go ahead and write the abbreviation for it. Power, which is going to be joules per second, which we call that the watt. And later on, we're going to see that we can take this power, apply it to some kind of time, and that's where we get the energy needed. And that's basically why is the reason to study physics. So when we talk about your energy, when you talk about your work, what is work? So let's go ahead and define work. Well, the work is defined as a force acting on an object equal of this force that you have multiplied by the distance that you do on this force. So let's say you got some kind of object and you want to move this object. That means you're going to have to apply a force on this object. This force is going to be used to move this object to some kind of distance d. This force times your distance, that's going to be your work. So your work, that's going to be your W, your F, that's your force, which is going to equal to your mass times your acceleration. And we already defined the displacement as your change in precision. In this case, it's going to be in the x-axis. So the work is defined as the applied force used on a distance let me just read this whole thing. It's the applied force used on a distance through the force acts on. Is the applied force used on the distance where the applied force acts on. So you're applying a force with some kind of mass. This is some kind of object with some kind of mass. This object is actually moving to another position from x initial to x final, which is going to be your distance. Now let's go ahead and look at this. So basically, your work equals your force times your distance, which we said that the force equals mass times acceleration. So is MAD. That's why I tell people it's very important to get a vacation when you do too much work, because too much work makes you mad. Your mass times acceleration times your distance or displacement. Now, your acceleration is going to be meters per second squared. Your mass, we discussed before, is going to be kilograms. And your displacement, we just mentioned a little while ago, would be in meters. So having to deal with the units is going to equal to the work, where the units is going to be, your mass is going to be your kilograms, your acceleration is meters per second square, and your distance is going to be another meter. So that's going to be another meter over here. So that means your work is going to be in your kilograms meter square per second squared. And that's, ladies and gentlemen, what we call the joule, which we give it a letter J, which is our unit for the work. So the work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance to which this object acts on. And that's what we just explained, where we explained that the work equals your force times your distance, which is your applied force multiplied by the distance to the force acts on. Now, it's important to understand that only the part of the force parallel to the displacement, to the axis that you're working on, contributes to the work done. So, for instance, let me go ahead and play our first movie. All right, we got the movie going on. All right, so here's our first one. So we said that the force equals your mass times the acceleration. So right now we have a low mass. So this is your little green ball, whatchamajig, going on over here. We have a force on behind it. Now, your force, your work is going to be your force times your distance. So we're applying the force, and notice that the further we go in the distance, the higher our work goes in. Is that force multiplied by the distance that is going on? So the force is keeping still, the distance is changing. That means the more the distance that we have, the more work that we do. In our next video, in this case, now we have twice as much force on it. And if you notice, that our work is actually increasing. So let's say we go and stop at the second light. Let's say we go back to our first video and let's go ahead. We go into our second line. There's a distance. In this case, we spend 20.402 joules. It's almost double on the other one because we have twice as force. Same mass, same distance, but this time because we have twice the force, our work done on the mass is twice as much, almost. Now, it's important to note that only the work parallel to the surface area does work. So let me just go ahead and show the third video. This time we have a force going on an angle. Because we have a force going on an angle, only the part that's parallel to the surface of the displacement is doing the work. So at this point, let's say we stop at the second. At the second one, let's go back a little bit. We saw that the work is going to be 14.34. On the same area, if it's going parallel to it, it's going to be 20.402 joules. So basically, for our third case, we had an object. This object was put on with a force vector V, and this is going to be your force directed at this displacement that's on the x-axis in order for it to go to another position. So from here to here, that's your D. That's your force D, which is, I'm going to go ahead and get the green one. So this is going to be your projection of the force F. And the direction of the displacement, which we called it FD. So that part only is doing work. Normally, you have an object with mass m that you go in. Let's say this is the same distance d, but this time the force is only directed parallel to the surface, which your work equals your force times your distance. So this is going to be higher than portion of it that's going to be only parallel to the surface. So your work equals your force times your distance, which means we just saw that the higher the force, the higher the work. Same thing. If the distance is higher, that means your work is higher. So either your force or either your displacement, that was going to determine if your work is going to be high or not. Now, as we just worked it out, the unit of the work is joule, which means it is Newton meter, which is kilogram meters per second squared. Now, let's say we have an object. Let's say we have an object. This is an object. This object is above ground. And now what's pulling this object down is going to be gravity. What else is pulling it down? It's mass. It has a mass of, the object has a mass. You know what? I'm just going to write that up. Which means what you got pulling it down? It's your mass times your gravity. Now it's going in from point A to point B. That means the distance between them, which we're going to call h for your height, is going to equal whatever final minus initial, which is b minus a. And that's where we introduce the work against the gravity. So in this case, your work is going to be your force times your distance. And in this case, it'll be what? Your mass times your acceleration times the distance. Now, what type of acceleration do we have? It's your gravitational acceleration, which is going to be 9.8 meters per second squared. Now, distance has a lot of names. What type of distance do we have? Is the height that you have in. And actually, let me actually just make this into a minus b, because a is b bigger in this case, because you just want the distance, which is the height, which is going to be your change in your position. So in this case, our work will be your mass times your gravity times your height. And this is going to be your work done against gravity. So your work is force here your distance, and again, your force is going to be your mass times acceleration, which in this case it'd be your mass times your gravitational force multiplied by gravitational acceleration multiplied by the distance, which we call height. So it's mgh. So let's go ahead and do an example, shall we? Now, before we do an example, I'm going to remind everybody with my 4 rules. So this is Dr. Malek 4 rules. And it's like Marvel. If you ever watch Marvel, you look at this. This is your Fantastic Four. So this is Dr. Malek Fantastic 4 Rules. Number one, write down the info. Number two, something is going to equal to your double question mark. Number three, you're going to write down the equation. And number four, like plug and play, this is called plug and solve. So we're going to be using this rule again to solve this question. So our question is, horizontal force of 100 newtons is used to push 20-kilogram box 10 meters across the level. How much work do you have to do, and how much work is needed to raise the same box by 10 meters? All right. So our first piece of information in this question, which is going to be your example 3.1a, is going to be our 100 newtons. So it's going to be our force. It's 100 newtons. The way you look at it, you just look at the number and say what it is. And the second one is going to be your 20 kilograms. Now, your 20 kilograms, that's going to be your mass. And your distance is going to be, your displacement is going to be 10 meters. And what are you looking for, part A? We're looking for the work. And knowing that your work is your force times your distance, in this case, it'd be 100 newtons times 10 meters. So it's going to equal to 1,000 joules. For part B, go ahead and look for part B. How much work is needed to raise the box inbox by 10 meters? So this time, our work is going to equal to mgh. You want to raise the box, which is going to be, actually, let me go ahead. It'll be your force times your distance, which is going to be your force is going to be your mass times your gravity multiplied by the distance. That's called your height. And in this case, it'd be your mass would be 20 multiplied by 9.8 multiplied by 10 meters, and you should get 1,960 joules. Wonderful. Now, so we have the work, which is your force times your distance, which is your mass times acceleration times your distance. Now, we take this work and we apply it to some kind of time, which is your W over your T. And that's what we talk about the power. So the power definition is the rate of doing work. Is the rate of doing work. So your power is going to equal to your work over your time. So your P equals your W over your T. Now, when we talk about units, the work is going to be in what? Joules, which we get the letter J. And your time, that's going to be in seconds. So this is going to be how many joules per second. And that's what we call the watt, which is which we give it the unit, the letter W for our unit, and that's going to be our unit for your power. So the power is defined as the rate of doing work, which is going to equal to your work divided by your time. Now, according to Newton's second law, the force is defined as new mass times acceleration. Because of the relationship between work and energy, whenever energy is being expanded, a force is being exerted. Now, your power is defined as your power is defined as your work over your time. And we define the work as your force times your distance. So therefore, the power is going to equal to your force times your distance divided by your time, T. Which is, if you break it down, it'd be your force times distance over your time. And we actually define the distance over time as your velocity in the beginning of this course. Which means that this power is going to equal to that force multiplied by the velocity. Wonderful. So let's go back over here. So your power is defined as your work over your time, which means that your work is your force times your distance. So your power is your force times your distance divided your time. And your distance divided by your time, that's your speed. So your power is also defined as your force times your speed. And again, when you have the power and you multiply it by your time, you get an energy. So when you actually define the energy, that energy can be thought of as the ability to do work. So let's go ahead and write this down. So when you talk about energy, it is the ability to do work. And again, your energy is going to be in joules. Now, the unit for power, which we just mentioned, is going to be watt, which is how much joules per second. 1 horsepower is going to equal 746 watts. So let's do another example, shall we? Let's say if you have a 15 kilowatt electric motor provides power for the elevator in a building. What is the minimum time needed for the elevator to raise 30 meters to the sixth floor when the total mass is loaded is 900 kilograms? So going in, let's go ahead and write down the information needed. So the first thing is we have is your 15 kilowatts. So it'd be 15 times 10 to the 3 watts. That's going to be our power. We also have your 30 meters, which you know is a distance. What type of distance? It's a height. And we have our mass, which is going to be 900 kilograms. And we are looking for your time. And now the third thing is we wrote down the info, we wrote down the question mark. Right now we write down the equation, which is your force times your distance. And in this case, it'd be your mass times gravity times your height. That should work. And you know that the power is going to equal to your work over your time, which means that is going to equal to mgh divided by your time. That means cross multiply, your t is going to equal to mgh divided by your power. And in this case, it would equal to your 900 for our mass, 9.8 for our gravity, which is a constant, and your height, which is 30 meters. Divide that by 15 times 10 to the 3. And plug in the mode in. That means your t should equal 117.6 seconds. Let's go ahead and check our answer. Yep, we get 17.8 seconds. So basically, energy is a property, something that has enabled it to do work. Now, when you talk about energy, there's two types of energies we're going to be talking about. The first one is called your kinetic energy, which we gave the letter Ke. Now, your kinetic energy is the energy that keeps on moving. It's your moving energy, kinetic. And this was going to equal, it will equal to, let me get a different color, 1/2 mv squared, or you can say it's mv squared divided by 2. The second type of energy we're going to be talking about is called your potential energy or your stored energy. So this is going to be your potential energy. And the potential energy is a stored energy. Now, the main one is your gravitational potential energy. PE gravitational, which is going to equal to the one we just saw, your mass times your gravity times your height. So energy is a property that something has that enables it to do work. Now, one of the first energies that we're going to be talking about is your kinetic energy, which is the energy of a moving object. If the energy makes you move. And we gave it the letter Ke. Now, the kinetic energy depends on two things, your mass and your speed, which is going to equal to 1/2 mv squared. Uh, Now, because this is energy, it's 1/2 mv squared. Let me go right ahead over here. So we said this Ke equals 1/2 mv squared. Now, in terms of units, let's take a look. The 1/2 is units. So it doesn't have a unit. the mass is going to be your kilograms, and your V is your velocity, which is your meters per second. Right now we have it squared, so it'll be meters square per second square. And basically we have the kinetic energy as in joules because it is energy. So any type of energy is going to be in joules, which is going to be your unit for your kinetic energy. So I just seen it's like it depends on two things: your mass and your velocity. So the energy, the kinetic energy depends on two factors: your mass and velocity. Which again, if you solve it, you'll still get the joule. So no matter what type of energy you have, you'll always be in joules for your unit for energy. So let's do an example, shall we? Let's do an example. What is the kinetic energy of 1,000 kilogram cars whose speed is 10 meters per second? So this is going to be example 3.3. So your mass is 1,000 kilograms and your speed is 10 meters per second. And this time you're trying to find your kinetic energy. And again, your kinetic energy, you write down the equation, which is going to be mv squared over 2. And in this case, it'd be 1/2, or I would divide by 2. It'd be 1,000 multiplied by 10 squared, divide that by 2, which is going to be 1,000 times 100, divide that by 2, which is going to equal to 50,000 joules, or to make it easier, 50 kilojoules. Let's go ahead and check our answer. Perfect. Now, let's do another example. Which object has the greatest amount of kinetic energy? 50 meters per second, 200 grams, 4 kilograms, for 7 meters per second, or 2,000 kilograms just sitting down in the parking lot. All right, well, let's take a look. So let's go ahead. This is our example. Part A. You got 20. Your mass is 200 grams, which has to be in kilograms. So convert that to kilograms. And again, let me just go ahead. You're going to go grams on the bottom. That way they cancel out. And you say 1 kilogram is 1,000 grams. So this is going to equal to 200 over 1,000, which is going to equal to 0.2 kilograms. We also have the velocity, which is 50 meters per second. And we're trying to find the kinetic energy. Let's see which one has the most kinetic energy. So let's find the kinetic energy for this one, which is mv squared. Let me go ahead and actually write down my question mark. And let's go ahead and solve it. Kinetic energy is going to equal to mv squared over 2, which in this case, it'll be 0.2 times 50 squared divided by 2. 50 squared is 2,500. So times 0.2. So it'll be 0.2 times 2,500. Divide that by 2. And you should get, for this one, 250 joules. Okay, let's do part B, shall we? For part B, you got 4 kilogram bowling ball traveling at 7 meters per second. So in this case, your mass is 4 kilograms and your velocity is 7 meters per second. Again, we're looking for your kinetic energy, and you know that the kinetic energy equals mv squared over 2, and in this case would be 4 times 7 squared over 2, which is 4 times 49 over 2. And so 4 divided by 2 is 2. 2 times 49 is 98 joules. All right, let's do part C. For part C, you got your mass is 2,000 kilograms, but this time you're sitting in the parking lot. That means your velocity is 0 meters per second because you're sitting down there. You're not moving. Velocity is distance per time. You're moving from one distance to a different distance in a different amount of time. That means your kinetic energy that we're looking for is going to equal to mv squared over 2, which is going to be your 200 times 0 divided by 2, and you should get, well, 0 squared, it doesn't matter. You should get 0 joules. So you would have no energy. So from the question that we had, which has the greatest amount of kinetic energy? Well, we had 0, we had 98 joules, we had 250. So our 250, that has the most amount of kinetic energy. Now let's go ahead and watch a movie. Notice it's for more distance with the same amount of force, same amount of mass, is just more distance. That means if she drops it down, it should drop the nail further because you're doing more work. So basically, the act of the hammer going down is creating the work. You're going from a force down to a distance. It is. So let's say we have another example, shall we? You got 0.6 kilogram hammerhead moving at 4 meters per second when it strikes the nail at 5 millimeters into the wood. What is the average force on the nail? And again, this is what we just saw. You get the hammer going in, has a mass, and it's going the velocity to a distance, which means it's going to have a work because using the force multiplied by that distance. So let's go ahead and set up our information in this question. So this is going to be example 3.4.1. So your mass in this case is 0.6 kilograms. Your velocity is 4 meters per second. And your distance is 5 millimeters, which is going to be 0.005 meters. Or you can actually, let me go ahead and just make it a little simplified. It'd be 5 times 10 negative 3 meters, which is going to be 0.005 meters. And you're looking for what? For your force. And now, in this case, you have, let me go ahead and get a new page. You have a hammer that is moving up and down. So this hammer, let's say this is our hammer over here. And you're going some kind of force and a velocity to some kind of distance, which means you have work done. And the work done is your force times your distance. Now, we do not have the force because that's what we need to find. We do not have the work, but we do have the distance. But the hammer is moving. That means it would have a kinetic energy, which is going to be mv squared over 2. So we can actually say that your work, which is your force times your distance, and what kind of work you're creating is your kinetic energy, which is mv squared over 2, which is your kinetic energy. Taking these two in, and let me just pull this up a little bit. That means your mv squared over 2 is going to equal to your force times your distance. And in this case, the force is going to equal to your mass times your velocity squared divided by 2d. And we have it from our information that your mass is 0.6 kilograms times 4 squared, which is going to be 16 divided by 2 times 0.005. And your force should equal to 960 newtons. Let's go ahead and check on our answer. 960 newtons. So that's your kinetic energy. Now, potential energy, it's a potential. It's a stored energy. For example, your gravitational potential energy, your spring, your electromagnetic, that's different types of potential energy. And your potential energy is defined, your gravitational potential energy is defined, as we just saw a little while ago, as your mass times your gravity times your height, which, again, your gravitational energy is where you started from work, which is your force times your distance, and your force is your mass times your gravity multiplied by the distance h. So your potential energy is going to equal to m times g times h. So let's say we have a question. What is the gravitational potential energy of a 1,000-kilogram car on top of 45-meter cliff? Let's go ahead. 3.5. Your mass is 1,000 kilograms, and your distance or your height is going to be 45 meters. And what are you looking for? You're looking for your potential energy, gravitational potential energy. And we define the gravitational potential energy as mass times gravity times your height, which is going to equal to your 1,000 that we have, times 9.8, which is your gravity, times your height, which is 45 meters, which means that our potential energy will be 441,000 joules, or 441 kilojoules. And check. Okay, that's awesome. Now, the potential energy is always measured relative to some point, whether either relative to the moon or relative to the floor, or etc. Now, energy can be transferred from one form to another. It can go from kinetic to potential, potential to work, etc. Now you cannot create energy, but what you can do is you can transform it from one to another, and that's what we talk about the law of conservation of energy, which is energy cannot be created. It can change from one type to another. So you cannot create energy. Energy cannot be created. It can be only transformed from one type to another. And again, this will talk about the conservation of energy. Energy may change from one type to another, but the total amount of energy in the universe does not change. You can only transform from one type to another. You cannot create energy. Many systems provide good examples. Transfer energy from potential to kinetic or kinetic to potential. So let's go ahead and check on a video.
Here is an arrangement called an energy well. The V-shaped bottom of this track is a potential well in which a ball can roll back and forth. If the ball has insufficient energy to escape over the top, it is trapped in the well and can only oscillate back and forth. How much higher than the low side would it have to be released from in order to escape?
How much lower than the higher side this energy is going to go? So we put the ball between the track, and the ball is going back and forth, back and forth. So the question that we have is the how high must the ball be released in order to escape? Below the low side, at the low side, equals low side, slightly above the low side, or much above the low side. So let's go ahead. Go ahead. A release point only slightly higher above the low side will be sufficient for the ball to escape because you're giving it that enough energy that is going to escape that hump. All right, then let's go take another look at another video. All right, here you go. So what do you all think? If the ball is released on that track, how high will it rise? Would it rise at the steepest on the first one, the least steep, the last one, or the middle one, or all the above? Let's go ahead and check the answer. because they're all released from the same height, it has the same amount of energy. So they all go to the same height on all three cases. So it's all the same. So the answer would be, let's go ahead and open up the presentation. It'd be all the same. All right. So one of the things that is actually apparent is Kepler's law. Now, with Kepler's law, let me go ahead and get my back to my little screen. Let's go ahead and get some more slides going in. So let's say this is our sun. That's our sun over here. And you got the Earth, and the Earth is going in a rotation mode around the sun. So when it's far away, that means your potential energy is at highest, your kinetic energy is at lowest. It's gonna come out when it gets closer to the sun. That means you have faster kinetic energy, higher. That means your potential energy will go lower. So you're gonna change from potential to kinetic. I think I have a movie to look about this. All right, here's our little movie. So here's our sun, here's the earth. Notice that's your total potential, total energy, that's your kinetic, that's your potential. So notice that the closer it gets to the sun, the gravity is pulling it in. That means you have more kinetic energy. Notice the potential energy is going down with the same ratio that the kinetic energy is going. It's going back to a full circle. Your kinetic energy falls down. Your kinetic energy is highest. Notice the total energy is still the same. Now, the best example about this would be the pendulum, which in a pendulum, so say this is my pendulum over here. Let me just go ahead, straight line. It goes back and forth. So when it's over here, your potential energy is highest, your kinetic energy is your lowest. And it keeps on moving where your kinetic energy over here at this point would be the highest it can be. Your potential energy is the lowest it can be. Going up, your potential energy would be the highest again, and your kinetic energy will be the lowest. So it moves in and changes between potential and kinetic energy. We got a video over here we can show y'all. So here's again, there's the kinetic energy, that's your potential energy, and that's your total energy. And notice that the total energy is almost the same. Kinetic energy changes. At this point, your kinetic energy is higher than your potential energy, and then you go back up where your potential energy is highest than the kinetic energy. So it's transforming from one form to another where your total energy is still the same. Okay. Now here's another movie for us to watch. Now, he's going to release the ball from in front of his face. Would it hit his face or not? Because it was released from the same point, so it only has enough energy to go the same distance to come back to the same spot. Right? Now, it's very important when you actually do this experiment to do it correctly, unlike this person over here. Yeah. The reason it hit him because he gave extra push, which gave it an extra force for the distance, which gave it an extra energy, and it came back with hit him in the face. So basically is the energy conservative. You cannot create energy. You can only conserve it from one form to another. In this case, it goes from potential to kinetic energy. Now we have another question. Let's see. So the total energy of the ball stays the same, but continues exchange between kinetic and potential, which we saw those movies. Now, let's do this question. A girl in a swing, 2.2 above meter of the ground, ends up in her motion at 1 meter above the ground, and her lowest point with the girl's maximum speed. So basically, it's like a pendulum. So here's a girl, and she's on this swing. This is example 3.6. So the height to the floor over here is 1 meter, and the height to the floor over here is 2.2 meters, which means that your displacement or your height is going to be your 2.2 minus 1, which is going to equal to 1.2 meters. And we are looking for the velocity of the girl. Now, with this, you're going between potential and kinetic. So you're going from kinetic energy and you're going to potential energy, which means your kinetic energy is going to be squared over 2, which equals to your mass times gravity times your height for your potential energy. And in this case, your masses cancel out, which means that V squared is going to equal to 2 times G times H, which means that V is going to equal the square root of 2 times G times H, which is going to equal to your square root of 2 times 9.8 times your height, which is going to be your 1.2. And solving for this, I got 4.8 meters per second. Let me go ahead and check our answer. It is 4.8 meters per second. Now, there's other forms of energy. You got your chemical energy, your thermal energy, electrical energy, radiant, mass, wave. There's different kinds. Now, uh, again, the law comes conservation of energy. Energy cannot be destroyed, created. It can be transferred from one form to another. It can go to from thermal to electrical to chemical, but it cannot be created. Now, one of the things that we want to talk about is the caloric, which was thought to be as a fluid or observation causing an object to warm. This person called Count Rumsfeld, which died in 1814, he was actually looking at boarding of cannons, which cannons exploding, and he decided to actually form an experiment where he actually put them underwater. Now he found out the large amount of heat when the cannon were bored was given off. Now this heat did not disappear; it was actually used to boil the water inside where he had the cannons in. Now heat could be repeatedly produced, which he one of the first people that actually recognized that heat is actually a form of energy. So when you talk about heat, it's a kinetic energy of random motion of the atoms and molecules of the body. The molecules of the body move. When they move, that heat happens. Higher energy, higher average kinetic energy of each atom molecule causes higher temperature of the body. We cannot say that matter contains heat but rather matter contains energy. So the amount of matter contains can be changed by the transfer of heat. Now, we also talked about Joule a lot. So Joule, the unit, came in as an honor of James Prescott Joule. He died in 1889, not too long ago. And he had a little famous experiment where he had a small pedal wheel inside of a container of water. And the I think I have a picture of it. Yeah, you have a small container, you have a small pedal inside a container of water, and we had a weight. Now he noticed that when the weight goes down, the pedal keeps on working. When the pedal works, the temperature actually increases. So he concluded that the work was done to turn the pedal. The friction heated the water, and the same amount of work was always produced the same amount of heating. And the thing about James Prescott Joule, he his dad owned a beer production company, and he was wealthy enough to actually go and study in college with Dalton, the chemist. And when he came back, he actually developed a new way to make the products at his dad's factory. And he's actually considered one of the first people, the grandfather of thermodynamics. So basically, James Prescott Joule discovered that heat is a form of energy also. Two objects of the same temperature have the same amount of thermal energy. Now, the common unit of heat of energy is the joule or the calorie, and heat energy is ever persistent. Whenever energy is being expanded, heat is always produced. Now, that brings us down to the linear momentum, which Newton's first law states that the object in motion remains in motion unless acted on upon a force. Now that's why I'm going to introduce something called linear momentum. So actually, let me just go and write down the word momentum. And we're going to give the momentum our Greek letter rho. And your momentum is how fast is something, I would say, coming towards you. And the way that this is acknowledged is going to be your mass times your velocity. So this is going to be your mass in kilograms and your V, that's going to be your velocity in meters per second. So if something has a big mass, so if we have two objects, let's say object one, object two, they both have the same mass, but let's say this one have a bigger velocity than this one. So basically M1 is going to equal to M2, which equal to M, but your velocity 1 is bigger than velocity 2, which means that according to P equals mv, more velocity, more momentum. That means there's going to be high momentum, and this one's going to be low momentum. Same thing. Let's say we have a mass. Let's say this is going to be a bigger mass. So let's say this is 2m, and this is one mass, m. And they both this time have the same velocity. Well, that's because this one has a bigger mass. This one's going to have bigger momentum. So this 2m is going to be bigger than mass, and you have the same velocity this time. Over here, you're going to have high momentum. Over here, you're going to have low momentum. So the linear momentum of a product is the product of the object's mass and velocity, and it's itself a vector. So in the absence of Outside forces, the total momentum is a set of objects remains the same no matter how the object interact with one another. So let's do a little example. So let's say this is our little example. So you got your mass. Let's say what was it? 40 kilogram girl running at 3 meters per second, jumping on a 10 kilogram sled that's initially at rest. How fast will she and the sled will be moving? So your mass is this time is going to be your 40 kilograms, and your velocity. So mass. Okay, so we got two. You got girl and you got sled. So the mass of the girl, I'm just going to call one is girl and two is sled. So M1, mass of the girl, is be 40 kilograms, and her V1 is 30, sorry, 3 meters per second. And M2, which is going to be the mass of the sled, which is 10 kilograms. That's initial sled, so that means V2 is going to equal to 0 meters per second. How fast will she be moving along with the sled? And in this case, your momentum before is going to equal to your momentum after. Now, the momentum before is going to be the girl mass. Actually, let me go ahead and write this down. It'd be the girl momentum plus the sled momentum is going to equal to the girl and the sled momentum, which means the momentum before, and let me go ahead and write this down on a different page so we can actually have it. All right, so the momentum for the girl will be your mass 1, V1 plus your mass 2. V2 is going to equal to whatever mass 1 plus whatever mass 2, and I'm going to call this your total velocity. And in this case, your V2 is going to equal to 0 because the sled is stationary. So your M1, V1 is going to equal to your M2, V2 times, sorry, M1 plus M2 times your V total, which means that the velocity that we are looking for is going to equal to which is your total velocity, is going to equal to M1 V1 over M1 plus M2. And in this case, it would be 40 times 3 over the mass of the girl will be 40 plus the mass of the sled is 10. So your total velocity, in this case, it'd be 2.4 meters per second. Awesome. Let's do another example, shall we? So in this case, this is going to be example 3.7. You got a 100 kilograms astronaut accidentally throws away a half a kilogram camera during a spacewalk. If the camera moves off at 6 meters per second, how fast will the astronaut will be moving? So this is example 3.7. So you got astronaut. I'm going to call this number 1. And the camera, I'm going to call it number 2, just to make it a lot easier. So you got a 100 kilograms astronaut. So you got M1 is 100 kilograms. Throw a camera, which is going to be M2, 0.5 kilograms. And then the camera moves, which is the speed of the camera, which is going to be 6 meters per second. How fast will the astronaut will be moving? So we're looking at D1. And in this case, your momentum before is going to equal to momentum after. Your momentum before is going to be your M1 plus M2 times your total velocity is going to equal to M1 V1 plus M2 V2. So in this case, your total velocity before was zero. So let me go ahead. Your VT is going to equal to zero, which means that this little fella will go to zero, which means that your M1 V1 plus M2 V2 is going to equal to zero, which means that your M1 V1 is going to equal to minus M2 V2, which means that your V1 is going to equal to minus M2 V2 over M1. And in this case, it'd be, and let me get a different color so it won't crash out, zero point 0.5, don't forget the negative, times 6, divide that by 100. And I'm running out of room. That means your V1 is going to equal to minus 0.03 meters per second. And the negative will still use the direction. That means it's going to the left side. And yeah, it's over here is going to the left at 0.003. Wonderful. So now, based on the conservation of linear momentum, the material expelled from a rocket engine is small relative to the mass of the rocket, but has a greater speed. Uh, Now, by building multi-stages rockets, engineers can achieve high final speeds. Empty engineers, structures, and tanks, empty engine structures and tanks are cast off the remaining vehicle needed to burn less fuel to accelerate. Now, when you talk about angular momentum deals with two things: your mass and your shape. Now, the angular momentum is conserved as the absence of outside torque. Now, if you ever talk about your spinning objects tend to maintain the direction of a spin axis. Now, Albert Einstein, which died in 1955, he did not die a long time ago, was the first to realize that the measurements of time and space are affected by the motion between the observed and the object being measured, which he developed the theory of relativity. The theory of relativity, his main equation is E is going to equal mc squared. E, that's your binding energy. Your m is your mass in kilograms, and your c, that's your speed of light, which is 2.99 times 10 to the 8 meters per second. And this is because its energy is going to be in joules. So let's do an example. Let's say you got a person that has a mass of 250 pounds. What is energy. All right. Well, first of all, we have 250 pounds that would need to be converted to newtons. And we know that 1 pound is 4.448 in newtons. We want to change 250 pounds into how much x. And now we take it, we cross multiply. So x that we're looking for is going to be equal to 250 times 4.448, which equals to 1100 newtons. Now, your 1100 newtons, that's going to be your force. And you know that the force is going to equal to your mass times gravity, which means that this mass that we have is going to be your 1100, your force divided by your gravity. And in this case, it'd be your 1100. And instead of not writing 9.8, I'm just going to use 10 meters per second squared. And it's going to equal to 110 kilograms. That means this energy, which is m equals c squared, is going to equal to your 110 kilograms multiplied by 2.99 or 3 times 10 to the 8, which is going to equal to 300 squared. Don't forget the square. So you're talking about 110 multiplied by 9 times 10 to the 18, and it's going to equal to 9 point, sorry, 10 to the 16, which is going to equal to 9.9 times 10 to the 18 joules. All right, let's go check our answer. 110. Yep, we got 9.918 joules. All right, let's do one more example, shall we? Let's with the amount of power given to each day a person consuming 1,500 calories per diet with no food. Okay, as fat. So this is another example. Let me go ahead and check this. So in this case, we got your energy is 1,500 calories. Now we need to change it. So we know that 1 calorie is 4.184 joules. We want to change 1,500 calories to whatever x in joules is. From this one, again, we cross multiply. X is going to equal to 1,500 times 4.184, which is going to equal to 6.276 megajoules. Now, they want it in 1 day. So if 1 day, to change it to seconds, you're going to have to multiply is 1 day is 24 hours, and 1 hour is 60 minutes, and 1 minute is 60 seconds, which the minutes cancel out, the hours cancel out, Days cancel out, and we have seconds. So our time is going to equal to 8,600, 86,400 seconds, which means we're looking for power. And your power is your work per time. And in this case, it'd be your 6.276 times 10 to the 6, which is your mega, divided by 86400 seconds. And you should get 73 watts. Let's check on our answer. Yep, 73 watts. So that's good. So the laws of physics are the same in all frame of references, moving at a constant velocity with respect to one another. And when you talk about frame of reference, when something is moving, the position of relative is something else. The frame of reference is changing. Now, the speed of light that we just talked about has the same value for all observers, which is going to be 2.99 times 10 to the 8. Sometimes you see it as 3 times 10 to the 8 just to make it easier. And we talked about Einstein energy formula, special relativity, which is E naught equals mc squared. So if I say how much mass is converted into energy by 100 megawatt nuclear plant, let's say in one day. So your time, this is our example 3.8. Your time is one day, and we just converted the one day, which is going to be 86,400 seconds. And our power is 100 megawatts, which is going to be 100 times 10 to the 6 watts. So our energy is going to equal to, which we just saw earlier, is your power times your time, which in this case, it'd be 100 one second before I actually let me just look at the question more time. How much mass is covered? So we're looking for the mass. It's very important to know what you're looking for. So we're looking for the mass. And in this case, you know that E equals mc squared, which means that the mass is going to equal to the E over c squared. Well, we have c, which is speed of light. We do not have the energy. So we need to find the energy. And we know that the energy equals your power times your time. And in this case, it would be your 100 times 10 megawatts, so times 10 to the 6, multiplied by 8,400. Then you should get your 8. You're moving the decimal, so it'd be 8.64 times 10 to the 12 joules. So this is going to equal to 8.64 times 10 to the 12 joules. Divide that by the speed of light, which is 3 times 10 to the 8. And you should get 9.6 times 10 to the negative 5 kilograms. Let's go ahead and check our answer. And our answer is correct. And that should conclude chapter 3 of the general physics for energy. If you have any questions, please email me at abunaemeh@gmail.com. Again, my name is Professor Malek Abunaemeh. Do enjoy. Have a nice day.